Okay, so before the break, where we were is we did a thin wall analysis, okay, of the 8 kilonewton shearing force coming in the Vx direction. Okay, so we realized that on element A, the shear stress is not equal to 0, whereas element B, the shear stress is equal to 0, because both the shear flow, right? Both the shear flow, our draw in, is coming towards the terminal, and it has nowhere to go. Okay, so that's why it's a terminal. So both, you can say one coming in from the top, the other one coming from the bottom. It cancel out one another. You can say that also. It's also a valid statement. Okay. Later on, I will teach you what is the shear direction later on when we do detailed calculation. Okay. All right. So the next one, the next view. So we have done what we can from this view, where we did not analyze the crosses, right? We only analyze the full arrow. Okay. So nothing else to analyze. We move on. So the next thing, we're going to look in the YZ plane. Okay. So from here, we are going to look at the YZ plane. Okay, so this is Y, this is Z, this is rotation in the X. Okay, and we are going to draw the structure. Okay, I'm going to sketch the structure out. Okay, so we're looking at it from the side view or end view, whatever you call it. Okay, and then we draw our position of our neutral axis. As I say, this is just a sketch for analysis. Okay, then we put in our element. So over here, this is our element A, right? Over here, this is our element B. Okay. Then we put in our associate forces. You got 100 kilonewton coming in here. You have 8 kilonewton. And then you have a 25 kilonewton. Okay. So let's deal with the difficult stuff first, so-called difficult, but it's not really difficult. Okay, I'll tell you what I mean. So the first thing we're going to do now is we're going to determine the moment, the moment in the X direction. Okay, so I'm going to state that going in a clockwise direction is positive. Moment in the X is equal. Now, moment in the X, this is where it's interesting. You have two forces inducing the moment. Okay, one is the 100 kilonewton. I want you to look at the direction. The other one is induced by the 25 kilonewton. The 100 kilonewton is parallel to the neutral axis. The other one is perpendicular to neutral axis. Okay, so what is the direction to use? Okay, not what is the direction. We know the direction. What is the value to use? So you need to know what is this distance. Okay, if it's parallel to the neutral axis, okay, so that's the distance. And the 25 kilonewton, this is the parallel, or this is the distance that you're going to take. Okay. Okay, so let's focus on the 100. The 100 is going to induce a clockwise. Okay, so 100. Okay, so the next distance is we have to find this distance over here. Okay, we have to find this distance. Then we divide by 2. So going back to our table, right? So the distance that we must acquire. So that is our distance D. D is 205. Okay, you can see that this is 205, right? So over here, you just put 0.205, 0.205 divided by 2. Okay, because the distance from here to, so the whole thing is 0.205 divided by 2. Okay, and then plus they're going in a clockwise direction, 25. Oh, I do apologize. It's 100 times 10 to the power 3. Okay, 0.205 divided by 2. So it's towards the neutral axis, then plus the 25 times 10 to the power 3. And then now the distance is towards the element. So it's 0.5. Right? Where I got 0.5 is over here. 0.5. So this will be equal to 100 times 5.205 divided by 2 is 10250 plus 25 power 3 times 0.5, 12500. So the whole thing is 10250 plus 12500 is equal to 22.750 or 22.75 times 10 to the power 3 Newton meter, and it's going in a clockwise direction. So a clockwise direction, so we know that this is your moment. Right, that is your moment in your x direction, compression, right? And then this is tensile. Okay, and then what's interesting, so we're going to apply stress X, or we will likely apply stress X is equal to mx over ixx multiplied by y, right? So for element A, it's going to be in a tensile region, right? Because it's on the left-hand side of the neutral axis. For element B, is equal to what? 0. Okay, so so the moment induced in the x direction will induce 0 stress on element B. Okay, by just looking at the moment, okay, it does not mean element B have no stress X. Later on, you still have the PZ over A coming into effect. Okay, then from here, anything else that you have to analyze? Nope. Then you know that Vy going towards the right, so Vy is positive, is equal to 25 times 10 to the power 3 Newton. Okay, now next we're going to analyze Vy. Okay, so again, Vy, we're going to look at the cross-sectional view again. Okay, so I'm going to take this image. Okay. So we know that Vy is coming in this direction. Okay, so this is our element A, and this is our element B. Right? So we sketch the shear flow now. So this is how the shear flow will look like. So these are our terminals. Okay. So what we realize over here is the shear stress. So we're going to find the shear stress is equal to Vy over Ixx, right? Qx over T. So from here, we know that at element A, the shear stress is not equal to 0. At element B, the shear stress will be at its what? Maximum. Okay? So this is the analysis that you have to perform in finding the shear force, or the analysis that you have to also consider, okay, while looking at the shear force, bending moment, axial force, and also looking at the torque. For this case, as I say, there's no torque. Okay, so we have completed the first part. Okay, so we have identified the forces and the associated stresses. Okay, so next we are now going to determine the stresses. Okay, so I'm going to do for element A first, then we're going to do element B. Okay, so let's consider element A. Anyone, any questions so far? I don't see any messages on the chat, so I think you are okay for now. Okay, so next we are going to look at element A. Okay, we're going to look at element A. Okay, we're going to consider element A. Okay, so the formula we're going to apply is stress Z at element A is equal to PZ over A, right, plus by mx over Ixx multiplied by y, plus by mz over, no, my, sorry, my over Iyy multiplied by x. Yeah. So our px, the value we have come up with, our px is equal to minus 100 times 10 to the power 3, as you can see over here. Okay. So we're going to write down minus 100 times 10 to the power 3. The cross-sectional area we got from the table, right? The cross-sectional area is equal to 5320 times 10 to the power minus 6. So this is equal to 5320 times 10 to the power minus 6. Okay, next we are going to look at mx. So let's see what we calculate for mx. Did we calculate? Yeah. So our mx is 22.75 times 10 to the power 3. Okay. So it's 22.75 times 10 to the power 3. Okay. Then you look at the direction. Okay. So we know that mx at A, so this is our mx, and element A is going to be what? Tensile. So it's going to be positive, which we have done down here already. Okay, which we have specified down here. So that's our positive. Then divide by our Ixx. So we look at our Ixx value is 40.8 times 10 to the power minus 6. Now, the next part is where students or even engineers will make mistake. What is the y direction? Okay, so if we look at our transformation, this is our x, and over here this is our y. Okay, so the y distance is relative to this y vector or transformation over there. So that is basically this entire distance over here, or this distance over here, right? Divided by 2. Okay, so we go back to our table again. Okay, so that distance is d, so 0.205 divided by 2. Right, so we have done the moment in X.